A moon orbiting a planet, a spinning Ferris wheel, a yo-yo trick called Around the World, the International Space Station. They've all got at least one thing in common.
Find out how they all come full circle next on Real World.
A moon orbits a planet, just like a planet orbits a star, in a curved, nearly circular path. A Ferris wheel curves around a central point as well. And of course, when you go around the world with a yo-yo, it's circling around your hand.
And why does all of this happen? Because of a little thing called centripetal force.
Basically, centripetal force is a force that makes an object, like planets or other satellites in space, follow a curved path. The word centripetal means center-seeking. What better place to study centripetal force than on the largest artificial satellite in space, the International Space Station? In addition to actually experiencing centripetal force, the freefall environment on board the ISS allows for some really cool demonstrations. So let's send it up to Expedition 22 astronaut Jeff Williams.
This is a tool. It's a special tool that we use on board the space station, actually during spacewalks. But it's a heavy metal object, and that's what I really wanted to use. And you can see I have it tied to a string, or with a string, onto this bungee right here. And it's just floating here in weightlessness. And you can see the string here is rather loose, and it's just kind of floating randomly. If I were to rotate this thing on the string around this bungee, and let me do this, you can see that the string pulls taut and stays tight, and the tool continues to rotate around the bungee. In fact, if you look really close at the bungee, you can see that the bungee bends at the point that it's rotating, and it bends toward the tool. And that is caused by the centripetal force due to the angular acceleration of the tool as it rotates around, keeping this string tight and keeping the rotation in a circular motion. It's the same kind of force that applies to the rotation of planets around the sun, or the moon around the Earth, or the space station around the Earth.
But you might notice that neither the moon nor the ISS is attached to Earth by a string, and they still orbit. Why is that? Well, think about this. Satellites would continue to move in a straight line because of inertia. Remember that inertia is the tendency of an object to keep on doing what it was doing before something forced it to change. Gravity is the force causing that change. Satellites in orbit around Earth are being pulled toward Earth by Earth's gravity. Acceleration occurs because gravity is continuously changing the satellite's direction. To understand how this works, take a look at this. I've got a yo-yo and I'm going to spin it around my finger on this table. The string here is acting like the force of gravity. If I let go when the yo-yo is at this top point, where do you think the yo-yo's inertia is going to take it? Will it continue in a circular motion? As you can see, the yo-yo wants to keep moving in a straight line instead of a curved one. That's inertia. The string is the only thing that held the yo-yo in its circular path. The string simulates gravity. In the same way, the ISS is held in orbit by Earth's gravity. If, for some strange reason, Earth's gravitational pull disappeared, the ISS would continue in whatever direction it was heading. Here's Jeff with another demonstration of centripetal force.
Okay, I've got this tea bag, and it's got tea in it, of course, and it's got air bubbles floating around here. The bubbles don't rise to the top in the absence of gravity in this weightless environment of the space station. But if I were to rotate this, and let's see if I can rotate it and keep it in your view of the camera. Let's watch what happens. If you look really close, you'll see the air bubbles starting to coalesce in the center of the tea bag. I'm going to try one more time. There's the bubbles spread throughout the tea, and if I rotate it, the bubbles coalesce to the center of the tea and eventually form a circle. Why do they do that? Because of the centripetal force spread throughout the tea. The liquid tea goes to the outside of the bags, and it forces the air into the center because the air has less mass, less density than the liquid. so the air goes to the center.
Centripetal forces affect things here on Earth, as well as in space. Things like Ferris wheels or the acceleration of a car going around the curve. But what other applications might this force have in space?
You've heard a lot of talk, perhaps, in regards to space exploration about artificial gravity. Perhaps you've seen some science fiction movies. For example, Star Trek, the TV show and the movies, they had gravity on board. They had some kind of a mysterious artificial gravity, make-believe, of course. But we've talked for years about artificial gravity on board a spacecraft, especially when you're going for a long period of time, for various reasons. One of the ways you could produce artificial gravity is by having a space station that rotates. Maybe very big, and the bigger it is, the slower the rotation would have to be to produce that centripetal force.
Jeff said that the bigger the station, the slower it would have to spin to create the centripetal force needed to make that artificial gravity. To find out why, we have to check out the math. Centripetal acceleration is equal to the velocity of the object squared, divided by the radius of the object. Spin is velocity divided by radius. The radius is the distance from the center of the circle to any point on the circle. The spin and size of the radius are actually in inverse proportion. On a spinning station, the larger the radius, the smaller the rate of change needed to simulate gravity.
Theoretically, you could do that. Theoretically, you could take a large station and produce, through centripetal force, sort of an artificial gravity to keep everything in its place. But the problem with that is when it's not very practical, because when you spin something and we turn our head around, our vestibular system will get a little bit messed up, and it's like if you're going around on a merry-go-round, riding a merry-go-round, then you step off the thing, or you spin around until you get dizzy. It'd be the same kind of thing. So I'm not sure artificial gravity in that way is very practical.
Wonder who will be the first to produce artificial gravity? But hey, don't just sit there and spin your wheels. Use that math to help solve this challenge. I'll see you next time on Real World.